15 seconds. Guidance internal. 13, 12, 11, 10, 9, 8. Ignition sequence start. Engines on. 5, 4, 3, 2, 1. All engines running. Launch commit. Liftoff. We have liftoff at 9:34 a.m. Eastern Daylight Time. The tower is clear.
And we have a roll program. Roger. We have good thrust on all 5 engines. Plane throttle, roll complete. Roger. And we have 50 program. Roger.
Hugh Blair-Smith from the instrumentation lab. And I guess the word is, it was the instrumentation lab, and then it was called Draper Lab in 1969. Is that when it was renamed?
More or less, yeah.
Okay.
What happened was that two things happened simultaneously. One is that in 1969, students decided that anything technical was going to be going to cause the end of the world, and started giving us all kinds of grief. And that was kind of the official reason for separating the lab from MIT, as much as it was, and renaming it Draper Lab. But I think the real reason, and maybe some of my colleagues can remember, is that it was politics in the Aero and Astro department. That was the dog, the lab was the tail, and the tail was getting rather large and started wagging the dog. And it was in the interest of the Aero Astro department establishment to have the lab move a little further away and be somewhat separate. And do you confirm that? Do we know? Yeah.
Something like that.
Okay. Anyway, there's a story. Before I get into this, there's a story I've been itching to find a moment to tell, and I'm very grateful to whoever it was that brought up the question of post-flight analysis. They brought it up, of course, with respect to Apollo. But the post-flight analysis story of them all was in the shuttle. The first approach and landing test was characterized by the first time we were running the 4 computers absolutely synchronized to run the control of the landing. And the 5x5 array of alarm lights, just the moment the shuttle popped off the back of the 747, the one, I forget whether there's a column or a row, but anyhow, one computer had clearly fallen out of sync. And the crew were trained to deal with this. They said, right, turn that computer off, and the other 3 flew the mission perfectly and landed exactly as it should be. So after that, the memory was dumped, all, however big it was, all hex digits, and several people were given copies to look at. And among them was a very bright light named Lynn Killingbeck, who had been IBM Owego originally. He'd come down to join the Houston, the IBM at Houston. And he looked at this for a while and he said, well, looks to me like the computer went bananas. And that was about as much as he wanted to say about it. And we had copies of this thing, and we looked at it and said, you know, there's this forest of hex digits. What on earth are we ever going to get out of this? Okay, so the computers came back, and the IBM hardware guys went over them, and there were these 2 big boxes, the CPU and the I/O processor, and this big cable harness running between them. And the cable harness was soldered at one end to the CPU, and the bad solder joint that had been jolted ran the highest priority interrupt, which went boing, 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 causing these enormous interrupts. And indeed, the computer went bananas. Lynn was absolutely right. And one of his friends thought this deserved to be honored, and this guy went out and bought 2 bananas from the grocery store, and with black marker marked them CPU and IOP. And he mounted them on a perfectly beautiful mahogany trophy base and put this on Lynn's desk. And that pleased him very much. But later that day, Lynn's management, dressed up like Klein there, came along and said, "Oh, well, Lynn, this is all very well, but you know, this doesn't do much for IBM's image. I suggest you eat the evidence." So, And so that's uh, that's how IBM was in those days. The attitude went with the clothes very much. The other disruptive story I want to do is the verb and noun in Shakespeare story, because I was hoping Ray would tell that, but I guess I have to. In the source code for the flight in the flight ropes, there is one set of remarks which is a genuine Shakespearean quotation, and what it says is, "It will be proved to thy face that thou hast men about thee, that speak of a verb and a noun, and such words as no Christian ear can endure to hear." Well, that's Dick the Butcher, and nobody remembers that part except those of us who remember that piece of the program. But Dick the Butcher is in maybe Henry VI Part 2, I'm not sure. And the thing he says just before that is, the first thing we do, we kill all the lawyers. And his problem with Lord Say was that Lord Say had founded a grammar school, and being a good know-nothing fellow, Dick the Butcher didn't want that. And that was his problem with verbs and nouns. So that was when the trouble with verbs and nouns really began. Anyway, I don't have slides here. I did try to persuade Rich to take all 700 pages here and make nice slides out of them, and he decided he'd better have a bit of a nap during the night instead of doing that. But he's undertaken to scan all this thing in eventually. So my piece is entitled YUL Pass Zero, and that's not because I really want to talk about Pass Zero, but because Pass Zero is the trunk from which all the branches of the YUL system operations spread out. The name, as I think we've kind of hinted, is the first computer, which was a 2-bit opcode, by the way. What there were 3 of was instructions, total, in that for a while. There was a 4th one. But that was the Christmas computer, and so I was told, right, we need an assembler for an unknown number of machines with unknown characteristics. Okay. In fact, it wasn't that hard because they were all kind of roughly similar in their architecture. And the first one's the Christmas computer, so, okay, you've been hired, September isn't over yet, get on with it, we need this thing by Christmas. So that was the YUL system, be ready for Christmas. Anyhow, it grew to do a fair number of things. The part called Pass Zero, let's see, I guess I should have this over here because I'm going to have to peek at the document. So let me know if I foul up with the mic business here. Begins by describing the various things you can do, and what you did. First of all the code was written, as this code was written, on punch cards, and punch cards, of course, came 3,000 cards to a steel case tray. I don't know how many pounds that weighed, but programming built men in those days, slinging these heavy trays around. So I included what was called director cards. That is, each deck that you submitted began with a director card, and it would say things like, assemble revision 112 of block 2 subroutine lead on by Macbeth, or something like that. So that it was an English sentence. It wasn't really a natural language processor because you had to have the right verbs and nouns, indeed, in the right sequence. And it gave both the program name and the official author. But late in the game, the official author just became a NASA drawing number. But so you could assemble a new program, you could assemble a revision, you could assemble a version from something else, sort of a save as operation. You could assemble a transferred program, and this is typical. There's an awful lot of things in here. I can't tell you anymore what some of the distinctions are. You can do a reprint, which simply recreates the listing from the last time. The listings were made on a 600 line per minute wheel-oriented printer, which accounts for the wonderfully low quality of a great deal of the print. And it obviously took a fair while, but that was the way you had to do that. And of course, this also served as a version control system. And you couldn't go back any number of revisions. The thing was kept on 3 tapes, the sort of Father, Son, and Holy Ghost. That is the current tape and the 2 previous. You could go back 2 revisions and collect a program if you'd really messed things up bad enough you wanted to do that. I don't think that ever happened, by the way. And I don't think we ever really lost a tape to mechanical failure that made that necessary. But it was a version control system. You had to get the right revision number, one more than the previous one. And you could delete things from the tape, and you could do, there was control and decontrol, and I don't even remember just what that was. You could print and punch. You could transfer things. And there's a great many operations like that. I just want to take you briefly through the architecture of this thing. Pass 0 would interpret, would parse these director cards and any subdirector cards that were necessary to specify exactly what's to be done. And that, as you see, is a fair amount of, that's documentation, a fair amount of stuff. But indeed, I filled up the memory of the Honeywell 800 doing that and had to put some stuff in as a sort of overlay. And being a good Apollo man, we call that the Pass 0 service module. So that's this stuff. And it handles a backup function, number of things like that. Now, I assume that most assemblers are still 2-pass. I know there have been 1-pass assemblers. But in this case, we had a sizable hunk of Pass 1 taking in the symbols, building a symbol table, and of course creating numerical values for the symbols, but not in the sequence that they could use right away, which is why there's going to have to be Pass 2. And the other thing that was kind of interesting, that the Honeywell 800 was in itself a multi-programming machine. It had 8 sets of central registers, and while there was only one physical arithmetic unit, these 8 things would all take turns. Some, of course, would be inactive. So part of what was here was what I call paraprograms, and one of them was in charge of reading tapes. Well, actually, each tape had its own, because at one point there were 2 tapes being written. One was in charge of writing one tape, one was in charge of writing another tape, and the other one was in charge of doing the actual processing. So the idea was to overlap I/O completely with processing. Lovely idea, only of course what happened was that the programs grew so large that the time waiting for the tape to spin kind of ate up all the time anyway. But anyway, so there was this parallel processing, passing buffers back and forth, sort of as if you build what is now called channel programming into this thing. Anyhow, that was the general part of Pass 1. And then, because this was for different computers, here's the part for the Block 1 AGC, just a few pages. What we've got here is kind of a table-driven kind of thing. Here's one for a thing called Sacco. There was a Sabre computer. I don't remember whatever became of that, but we were going to make a variation for the Sabre. What was Sabre? Anybody remember? It was a kind of missile system, I think. And then there's the Block 2 one, and then I forget just why, but we made a variation on Block 2, which we simply called AGC. I just had a 4-character name to identify which the thing was. And finally, there was a very trivial thing, which made this thing into a just a listing manager, kind of a documentation program. I don't quite dare say word processor, but you could simply create documents and have them managed by the same thing, the way the programs were. So then Pass 2 came along and used the completed symbol table to fill in all the values and put the completed but not yet sorted code on a tape. And I guess it wasn't fully completed, but it was, in any case, each instruction was converted into binary at that point. And again, that had had its parallel programs, and had its little specialized piece for each computer. Again, a sort of a table-driven arrangement. And in here, I implied before that I wrote this whole thing, but that isn't quite true. Because at some point, we had to have assembler logic for the 100 and, I don't know, maybe 115 interpretive instructions, some of which were really wonderfully juicy. Matrix times vector. You need an instruction like that. And the interpretive code was consisted of a pair of 7-bit opcodes, plus, of course, a bit to show this was an opcode word, followed by as many 15-bit addresses as were necessary for those opcodes. And so the interpreter went through that and performed the vector operations. It performed some of the multi-position operations, and had something more like emulated real index registers, which of course we didn't have in the machine. Anyhow, so all that needed a helping hand, and a fellow named Cliff Ide, a wonderful, brilliant fellow, came along to do that. And he was one of these fellows who can write you a patch of code in a couple of days, but without any comments. So that when you wish to read this thing, it takes you at least an order of magnitude more time to read it than it ever took him to write it. But nevertheless, he was absolutely brilliant, and the stuff ran. In fact, I'll make, on behalf of Cliff and myself, a small boast. I think I only remember one bug being kicked back to us from the users in the lab of the system. I think we managed to make this thing sufficiently ironclad that there was only one complaint. Maybe somebody can remember more than that, but that's all I remember. So that was the main part of the assembling process as such. Except there was finally the business. We had all this stuff on tape. The Honeywell did acquire a disk drive later, which was a wonderful machine. The disks were about so big around, and about so thick, and there were maybe 16 of them. And the machine that ran them sat on one side of the room, and when the actuator was moving the read-write heads from one track to another, it was like an earthquake that was going on. This was a mighty machine. It was really wonderful. But it was so hard to use in the absence of a disk operating system that I never had time to actually exploit it for sorting. So the sorting and presentation of the final tables, and there were quite a lot at the end of the listing, was done by what I call Pass 3. And again, it had specialized pieces as well as the generalized one. Then I never called this Pass 4, but there was another aspect of this thing which was called manufacturing. And what that did was it created the paper tapes, only they weren't really paper, they were Mylar. And if you think of the picture that I think Ray was showing here of the lady sticking the needle through the rig there, the white thing in that picture was a funnel, and it stayed in one place. And what the machine behind it did was to shift the frame with the cores in it this way and that. And so that's what my punch tape drove. And that was the output of the manufacturing process to do that. And the first thing that I did with that was to produce a tape that created the inhibit lines, which were simply defining which core was which address. And when that worked, people thought, well, okay, maybe it will be all right to let this thing run the weaving of the ropes. So it was nice to have that confidence. And finally, there's the piece that never was, really. But early on, obviously there had to be two major support software items. One was this whole assembler version control manufacturer. The other one was, of course, the software simulator, or emulator, as we'd probably call it today. And that grew up, of course, into a fairly elaborate program. It had to have a lot of punch cards specifying what the astronauts were doing and when, what buttons they were pushing, and all that. But before that was ready, with the help of a young lady named Judy Vogel, I have no idea what became of her, I made a very simplified version. And the only reason I mention it is that it contained a feature that I would love to see today. You will often hear references now to trace buffers, and sometimes these are in hardware. In fact, we had one called the Coroner with the AGC. But the simulated trace buffer in here had a feature that maybe somebody else has done it. I hope somebody has. It had a loop detector. And that is to say, whenever it put the results of an instruction into its buffer, it first looked around and said, have we been here before?
Yeah, get on landing. Planes total, roll.